You add a cron job, one line. Run this every night at midnight. It works perfectly on your laptop. Then you deploy to production, running on 3 servers for redundancy, and at midnight the job fires 3 times. 3 duplicate emails to every customer, 3 charges. That's the entire distributed job scheduler problem in one sentence. The moment you have more than one machine, run this once becomes astonishingly hard. Designing a job scheduler is asked at every senior and staff interview because it's a trap disguised as a to-do app. It looks like a queue and a timer. It's actually a masterclass in the hardest problems in distributed systems: coordination, failure, and the impossibility of doing something exactly once. And that's the spine of the whole design and the single most senior thing you can say. Exactly once execution is a myth. You cannot guarantee it. What you actually build is at least once execution plus idempotency. If you don't know the difference, this interview ends early. Clarify first. Job scheduler hides several different systems. Functionally, submit a job to run once at a future time or on a recurring schedule. Execute it reliably. Retry on failure. Let the user see status and cancel. The clarifying questions that signal seniority: precision. Must jobs fire to the second, or is within a minute acceptable? Execution semantics. At least once or at most once. For most business systems, it's at least once plus idempotency. Now quantify. Scale. 100 million scheduled jobs with peaks of tens of thousands firing per second. Midnight and top of hour are brutal because everyone schedules daily at midnight. That thundering herd is a real constraint. And state durability as a contract. Target 6 nines. A job the system accepted must never be lost, even in a total data center power failure. So jobs live in durable, replicated storage, not memory. A quick estimate: 100 million jobs at about a kilobyte each is 100 gigabytes of metadata. Fits a sharded database. 10,000 dispatches a second means roughly 10,000 workers at peak. Here's the framing that organizes everything. A scheduler is 2 planes. A control plane that plans and persists intent, what's due and who owns it, and a data plane that executes and reports back, the worker fleet. Grow the fleet without touching the planning brain, and an execution storm can't corrupt the source of truth. The API is small. Submit job, cancel job, get status. The data model is where it starts. A job row with an ID, payload pointer, run at time, schedule, status, attempt count, and a locked until field for failure handling. Now database versus message queue, where people hand wave. Why not just a message queue? It delivers now, roughly FIFO. It has no native deliver this at 3 p.m. next Tuesday, and you can't query it to cancel or reschedule. So a queue alone fails as the source of truth. Why a database? Relational gives durability, queryability, and the atomic claim we'll need. No SQL scales, writes, but makes the atomic claim harder. Pick it only at extreme write volume. And the hot partition trap most people miss. Every scheduler polls where run at is less than now, hammering the same narrow slice of the index, and midnight piles millions of rows on one timestamp. Fix it by sharding by hash, not time plus jitter. So the architecture is a split. The durable database answers what's due and who owns it. A queue answers hand this to a worker fast. Each does what the other can't. How does the scheduler know a job is due? Naive database polling. Every second, select where run it is less than now. Simple, durable, fine at modest scale, but it hammers the database every second, and polling interval bounds your precision. A push or delay queue lowers latency, but caps how far out you can schedule and isn't durable alone. The staff-level answer is the timing wheel, borrowed from OS kernels. Imagine a circular buffer of slots, each a tick of time. 1 slot per second, 3,600 slots for an hour. A job due in 5 minutes goes in the slot 300 ahead. Every tick you advance 1 slot and fire everything in it. Order 1 to find what's due, instead of scanning a table. Hierarchical timing wheels handle long ranges, a seconds wheel, a minutes wheel, an hours wheel, cascading down like clock hands. This is how Kafka's Purgatory manages millions of timers. The trade-off: the wheel lives in memory for speed, so it must be backed by durable storage. On restart, rebuild it from the database. The pragmatic real answer is a hybrid. The database holds all jobs, and you load only the near-future ones into an in-memory wheel for precise firing. You don't hold 100 million timers in memory, only the imminent ones. Here's the core. Problem 1. Multiple schedulers, one job. For availability, you run several. But if all see the same due job, they all fire it. Duplicates are cold open bug. 2 fixes. Leader election, elect one scheduler to dispatch via Zookeeper or a database lease, or partition and atomic claim. Shard jobs across schedulers and let each atomically grab a job. The production mechanism in Postgres is select for update skip locked. A worker locks a batch of rows and skip locked makes other workers instantly skip them, so N workers pull disjoint batches with zero contention. That clause is the difference between reading about this and building it. Problem 2. The worker crashes mid-job. It claimed the job, started, then died. Now it's stuck in running forever. This is the visibility timeout. On claim, set locked until to now, plus a timeout. If the worker finishes, mark it done. If it crashes, the lock expires and the job becomes claimable again. Too short and a slow job gets duplicated. Too long and recovery is slow. Which is the whole point. Exactly once is impossible, because you can never know if a timed-out worker died before or after sending the email. So you choose at least once, always retry, and make jobs idempotent, so a duplicate is harmless. And for a poison job that always fails, exponential back-off, max attempts, then a dead letter queue. The midnight thundering herd, 10 million jobs all at midnight. You can't fire them in 1 second. Add jitter. Spread daily at midnight jobs across a window with a small random offset. Shard the dispatch and prioritize time-critical jobs. Now the question most people miss: multi-tenancy. In a shared scheduler, one noisy tenant who schedules 10 million jobs can monopolize the worker pool and delay everyone else. The noisy neighbor problem. A plain FIFO queue has no defense. The fix: per-tenant quotas and weighted fair queuing, so the dispatcher round-robins across tenants instead of draining one tenant's backlog first. Dedicated shards for your biggest tenants. And make jobs idempotent for real. An idempotency key table, the key inserted atomically with the side effect and pushed downstream so even external calls dedup. What about jobs that depend on other jobs? The airflow question? Now, you're scheduling a DAG. A job becomes eligible only when all its parents succeed. And would you build this from scratch today? The staff move is knowing when not to. Durable execution engines like Temporal, born from Uber's Cadence, or DBOS, built right on Postgres, now provide durability, retries, and crash recovery as a primitive. You write the workflow as code, and it resumes exactly where it stopped. So, simple periodic jobs, the design we built, complex long-running workflows, adopt a durable execution engine, rather than reinvent retries. And observe it. Dispatch lag, retry rates, dead letter queue size. The key alert is jobs firing late. Let's zoom out. Exactly once is a myth. Build at least once plus idempotency. Durability is sacred. A durable database is the source of truth, not a queue. The queue is for dispatch. Prevent duplicate firing with leader election or partition and atomic claim using select for update skip locked. A timing wheel backed by storage finds due jobs efficiently. Visibility timeouts recover jobs when a worker crashes. Back off, max retries, and a dead letter queue handle poison jobs, and jitter the thundering herd. Separate scheduling from a scalable worker pool, and use DAGs for dependencies. Master those, and you can design a scheduler on any whiteboard and defend every failure case. But knowing it and performing it under pressure are different skills. Practice this exact interview with an AI interviewer that pushes back like I did at crackit.io, free. Design the system, then go defend it. See you in the next one.